Welcome to Design of Concrete Structure course. So this is lecture number 13. So up to lecture number 12 we have discussed about beams. So initially we discussed about single reinforced beam design, and then later we have discussed about doubly reinforced beam, and then in the last class we have discussed about the shear, how to design the stirrups and how to take care about the shear forces on a beam that we have discussed in details. So now in this lecture 13 onwards we'll be starting. So this and next two lectures will be discussing about the slabs. So as I mentioned in earlier lecture, at the beginning initial lectures, the primary elements of any building, if you see, so there will be slab. Number two is beam, and then we have column. Number three is column. Number four is footing or foundation. Footing. Okay, so these are the basic four primary things, primary elements on any structure. So in earlier already we discussed about the beam part, how to design the beam that we know. So in this lecture and next few lectures we'll be discussing about the slab design, and then later on we'll be discussing about column design and the footing and foundation design. So this completes a complete structure. So if you consider, if you see any structure, it may be a building, bridge or building, whatever it may be, it is composed of these four elements: slab, beam, column, and footing. So loads are transferred from slab to beam, then beams are connected in a column, then column is ultimately resting on a footing. So that's how the load is transferred from slab to beam to column to footing. So if you understand each component or each element of a structure individually, then if you combine all, you will get the entire structure. So similarly for bridge also, you will find the loads are transferred on a bridge deck, which is nothing but a slab, and through then this bridge deck is actually resting on a beam, and through beam the load is going to the pier, bridge pier, and ultimately through foundation the load is transferred to the soil. So that is a typical load path of any structure. So now in this lecture we'll be discussing about the slab design. So let's get started. So before we start about slab design, let's understand the different types of slab here. So now if you consider, this is a simple beam, simple slab where four side four beams are there. So what are these four beams? So you have this one beam here, another beam, this vertical beam, this is another beam, and this is another beam. So four side you have the four beam, and four column are also there. So here you have one column, here another column, so here another column, and here also we have another column. So now you understand there are four sides and the four columns are placed. Column 1, column 2, column 3, 4, and 4. So in this four column, basically beams are connected. So this is first beam, we have second beam, third beam, and then fourth beam. So these four beams are actually resting on this column. So now above these beams, four beams, we have the slab. So this is one slab. So now this slab, if you see, one dimension is less compared to other dimensions. Okay, so this Ly is the length in y direction, Lx is the length in the x direction, and these are the end support. So this is a very simple case where you will find only four beams will be there and the slab is resting on it. And now if you see, this one dimension is very less compared to this dimension. So in that case, that beam we call it is a one-way beam. If one dimension is very less compared to other dimension, or in other terms, if Ly by Lx is greater than 2, then we call it is a one-way slab. So we'll discuss in more details what is one-way slab, but for the time being, let's understand what is one-way slab. So if one dimension, either it may be Ly or it may be Lx, whatever it may be, if one dimension is more than double of another dimension, then this type of beam we call it one-way beam. And typically you will find this type of beams, and this beam, whatever I am talking, this slab is simply resting on the four beams. Okay, so this is one type of slab, we understand. So now if you see this dimension, so that's the same structure. Now if you add one more bay here, one more frame, portal frame in this direction, then you will get this type of structure. So in that you will have the beam is resting on these two end support. So these two are end support whereas this side the slab is continuous. So if you see, multiple supports are there, but the slab is continuous here, unlike here. So here slab is not continuous. In all sides you have the edge, right? All four directions it is end, right? So that's why it is called end support. So these four are all actually end support, whereas in this case these are actually end support, whereas this middle one is not end support. These are intermediate support, because here the slab is continuous. So from slab is running from one left to right. So this is a typically you will see in any structure where the slabs are actually continuous. Beams are also continuous beams here, but here the beams are also not continuous beam. This is a, you know, it has it is a discrete beam, whereas here the beams are continuous beams. Slab also continuous, but in the one direction, towards x direction. But again in the y direction it is discontinuous. The beam and slab both are discontinuous. So, and this is another type which you will see in normal real life structure, where in any multi-story building, if you are sitting, you will find this type of structure where this fourth side you have the four periphery beams, or we call it primary beams, and in the middle you have the secondary beams and columns also at the center. And these are the intermediate support, which is towards x and towards y, both directions. Here it is there, but here we intermediate supports are there only in about the x direction, right? And here it is about both the directions. Intermediate supports are there. So each panel, design of each panel will have different criteria, because see, if you design this panel, this slab, so this side is continuous, this side is continuous, whereas this side is not continuous, that side also not continuous. Similarly, if you consider this beam, here three sides are continuous. This side is continuous, this side also continuous, this side also continuous, whereas the left side is discontinuous. So each panel, if you see, each panel of the slab will have some properties. Like if you consider this middle portion, so here all four sides of this slab are actually discontinuous. Continuous. Okay. Whereas in the corner slab panels are actually continuous in two age, whereas two discontinuous in another two age. So depending on the panel where it is, whether it is continuous or discontinuous in one side and all, then the beam design will vary. So that we'll see in the latest slides how this effect has to be considered. So now you understood there are basically two types of slabs are there. One is one-way slab, one way, and another is two-way. So these are the two types of slabs are there. So which one is one way? One way slab is if one dimension is more than double of the second another dimension, then we call it is a one way slab. Like here if you see, this dimension is very long compared to Lx. So that's why this beam is actually a one way slab. Whereas if you see here, each panel, this is one slab, this is another slab, right? So and if you see, both the dimensions are almost equal. Lx and Ly both are almost equal. So in that case, if Lx by Ly is less than 2, then we call it is a two-way slab. If Lx by Ly by Lx is greater than 2, means it is one way, and if it is less than 2, then we call it is a greater than 2 means it is one way, and less than 2 means it is a two-way slab. So now here in details, both the types are discussed, one way and two way slab. So let's investigate more in detail. So here you consider this is a beam, four beams are there, one, two, three, and four. So four column, one, two, three, four columns are there, and four beams are also there. Okay, so this is a very simple rectangular structure. And now you have at the middle one, two, three, four. This is the actual slab part. So as we discussed earlier also, this slab, how to differentiate the one-way slab or two-way slab? Basically, Lx and Ly, we have to find it out. Lx by Ly, that ratio, if you find it out, then this will give you whether the slab is one-way or the two-way slab. So anyway, so now you understand here, one, two, three, four columns are there, and in that four column, basically the slab is resting here. So now how the loads will be transferred to the beam? As I mentioned in the first slide also, how the loads are transferred. Loads are transferred from slab to the beam, then beam to the column, and column to the foundation, right? This is a typical load path of a beam, of a structure, right? So now the entire load will be there, right? A load of a floor. So how much load will go to this beam? So as I mentioned here, the four beams are there in four sides, isn't it? So this is beam 1, beam 2, beam 3 and beam 4. So four beams are there in four sides. Now how much load will come to beam 1? How much load will come to beam 2? How much load will come to beam 3? How much load will come to beam 4? So that how can you find it out? So entire load will be actually resting on the slab. Okay, it may be UDL or UVL, whatever it may be. The entire loads will be resting on this slab. Now from this slab, how much load will come to this beam? So from this slab, how much load will come to this beam? Okay, like that all four, how will you do? So that our IS 456 has given the area or the distribution, how the loads will be transferred from slab to the beam. So how we have to do it? Basically from 1 to 2, we have to make 45-degree angle, 45-degree angle line. So this line, we have to draw it 45-degree angle line. So here also from second point, we have to draw the 45-degree line. So when both the points are meeting, that is basically a triangle. You will get it, this type of triangle, and the angle is 45 degree. Similarly, same thing you will get it in this portion also. Okay, now you connect it at the middle portion, something trapezoidal section will come in these two sides. So now as per our IS 456, this triangular portion load will be coming to this beam. This trapezoidal portion load is coming to this beam, second beam. Again, this triangular portion of more load will be coming to this beam, and again this trapezoidal section of the slab load will be coming to this beam number 4. That is, as per our IS 456, you will get this load distribution for slabs. So now what you understand is, if what happens, see, if this Ly is very very high compared to Lx. If Ly is very long, what will happen? What is the area of this triangle? So this area of this triangle will be more further reduced. If you compare, what is the area of this trapezoid? It is very high, right, compared to this triangular area. That means this column or this beam actually will carry very less amount of load compared to this beam, because this entire trapezoidal area load will be coming to this beam, whereas this entire triangular area load will be coming to this beam. So obviously this triangular area portion is very less compared to this trapezoidal portion, is not it? So here the load is very less compared to this one. So here more load will be coming. Okay, now if Ly is further more, if Ly, this length, this length, if it is very long compared to this one, then what will happen? This area of triangle will further reduce, and this area of load will be much negligible compared to this triangular shape. So that's how the bending will happen. So when the load is applied here, basically what happens? The slab will deform, right? Slab deformation will take place. So now it has two directions, right? X-axis and Y-axis. Now you understand this beam, the shorter direction, only the triangular portion load is coming here in this beam, whereas the longer the edge of the slab, basically this trapezoidal portion load will be coming. So the distribution or the deformation, basically deformation of this portion of this along the y-axis, how much it will be? So it is somewhat constant. See the load here. Load is almost constant in this beam, is not it? So although only if you neglect this small portion, otherwise this entire beam will have a constant load. That's why the deformation also, if you see deformation of this y-axis or y portion will be something like that. It is constant from center to here. After it is maximum portion, it is flat, constant deformation you will see. Whereas at the edge you will see the deformation maybe a little less, because of at the edge loads are comparatively less. Otherwise it is a constant. So middle portion is entirely constant. This is the deformation curve of the slab towards y-axis. Whereas about the x-axis, how it will deform? So about the x-axis, if you see at the center of the beam or at the center of this location, basically the load is the deformation is maximum. So this is the deformation shape you will get it, because here load is maximum, means deformation also will be maximum. Okay, similarly here load is less, so deformation also less. So this is the typical deformation about x-axis, and this is a typical deformation about y-axis. So now you can understand this one way beam or one way slab basically tackles the load by bending primarily. So primarily it bends towards the shorter axis, but towards the longer axis, towards the y-axis, the bending is very less. It is constant at the center, isn't it? Whereas towards the x-axis, you will see the bending. Similar thing about beam, what we have seen earlier lectures. So if you apply a load in a beam, how beam buckles? So this is a UDL is if it is applied, and this is a beam, simply supported beam, and how the beam will buckle. So beam will buckle something like that. Okay, so this is a typical buckling shape of beam, right? So now also here also you can see about the shorter span of the slab. Basically, the deformation is basically similar to the very similar to the beam. So that's what, so whatever load is applied on a slab, so in the longer span or in the longer direction, if it is a one-way slab, means longer direction, the deformation is almost constant. Whereas in the shorter direction, the deformation is parabolic deformation along the short span, you will find it out. So this is about one-way slab. Now what about two-way slab? So two-way slab means when the Lx by Ly is less than or equal to 2. That slab we call it two-way slab. So at the first instant we have to find out which type of slab it is, whether it is one-way slab or two-way slab. So how will you find it out? Very simple, Lx by Ly we have to do it. If it is less than 2, then it is a two-way slab, and if it is more than 2, then we call it as a one-way slab. So two-way slab means Lx by Ly is less than or equal to 2. That means both the dimensions are actually similar. Okay, whatever may be the Lx and Ly is almost similar. It is simple square you can consider. Whereas this one is more into rectangular slab. So now, so as I mentioned here, both the dimensions in the 2A slab are very much comparable, means very much similar. So that's why the bending, whatever, so the distribution, if you see as per IS code, the distribution is same. So 45-degree angle, it is there. So 45-degree angle you have to draw, 45 angle you have to draw. Similarly, here also 45, here also 45. Now this triangular portion load will be coming into this beam. This entire trapezoidal portion will be coming to here. So similar thing will be happening. So as I mentioned here in two-way slab, this dimension, both are very similar because Lx by Ly should be less than equal to 2. So the area here and area of this trapezoid is not much varying compared to one-way slab. So one-way slab, if you see, the triangular portion is very negligible compared to trapezoidal portion. Whereas here both are almost equal. So because of that, the deformation also will be something like that. In both axes, you will find the deformation. So this is one way axis and this is y axis. The deformation, parabolic deformation curve you will see in the long span and short span, both directions. So that's why the name of this beam is actually called two-way slab. Two-way slab means basically the deformation is happening in the both the directions, x direction as well as y direction. Whereas this is, we call it one-way slab because the deformation is happening only at the one axis. Either it may be x or it may be y, whatever it may be. The deformation, beam deformation. So now the design of slab is also very similar to design of beams. Why? Because in the beam also, if you see, what is the difference between slab and beam? So if you see in this beam also, the loads are acting, transverse loads are acting, UDL, UVL, whatever it may be, but transverse loads are acting on a beam, is not it? And each beam also will be resting on a support. Similarly, slab also, loads are acting, transverse loads are acting, and it is resting on a beam. So the design of slab and design of beams are also very similar, and whatever problem we'll be solving today, one-way slab design and beam design is exactly identical. That we'll see in the next slides. Whereas design of two-way slab is little difference from the beam design, conventional beam design. That also we'll check it. So what we understood from here is Lx by Ly, if it is more than 2, then we call it a one-way slab. So one-way slab means bending will be happening only about one axis, and bending always or only happening about the short axis. Whereas if the Lx by Ly is more than, or sorry, less than or equal to 2, then we call it is a two-way slab, where here the bending is happening about the both the axis, short axis as well as long axis, both the axis bending will be happening. So that we understood from this slide. So now let's check what about the design shear strength of a concrete. in a slab. As we mentioned in the earlier classes also, that slab basically, this is a simply rectangular slab, and UDL is acting, right? UDL is acting on a slab. So because of that, basically the bending moment and shear force both will be generated, right? Bending moment and shear force both will be generated in the beam or in the slab basically. So now bending moment, for taken care about bending moment, basically we have to provide the reinforcements at the bottom as well as the top, right? Similar thing what we discussed in the beam design also. But what about shear? So if you look into real life beams or real life columns basically, or real life slabs, if you find real life beams will have much deep section. That's why we provide stirrups also. In the last lecture I discussed in details about stirrups. So stirrups are actually required to take care about the shear stress. If more shear stress is coming into the beam, then we have to provide the stirrups on a beam, and at a at a certain interval we have to provide it. But whereas in a slab, if you see, the thickness of the slab is normally 15 centimeter to 20 centimeter. It is not as deep as a beam. And normally if you see stirrups, we won't provide in a slab. If you see any real beam nearby to you, normally we won't provide stirrups into slabs. Now why? Because the shear stress on a slab is very less compared to shear stress on a beam. Why? Because in beam, basically the thickness of the beam or the width of the beam is less, whereas slab is very, wide area you will find it out slab. That's why the shear stress on a slab is very negligible compared to beams. Because of that, we won't normally generally we won't provide the shear reinforcement or the stirrups on a slab. Although for design of culverts or the bridges, or if you see the flyovers in cities, there maybe sometimes they provide stirrups even in the slab, because there the loads are very high. Now in a beam or in a bridge, basically the heavy vehicles are moving from one end to another end. So because of that, the heavy concentrated load will be coming into the bridge deck. Because of that, shear stress also will be very high. That's why in a bridge deck sometimes, or in a culvert basically, sometimes we provide the shear reinforcement. Or in a flyovers normally sometimes we provide the shear reinforcement with the stirrups on a slab. Whereas in normal buildings, normal residential buildings, or maybe educational buildings or hospitals, where their loads won't be that much severe in compared to bridges or flyovers. So because of that, shear stress is always within the limit, and that's why we don't provide shear reinforcements in the slab. So in the table 19 of IS 456, we'll give you this table. So what is this table? So this is the overall depth of the slab. So the shear stress, basically tau c on a slab, is normally depends, or shear stress is depends on tau c, is actually tau c multiplied by k. If you multiply tau c, that is shear stress, multiplied by k, then you get the actual shear stress on a slab. Now what is k? So k is a factor from this table, basically table 19 IS 456. If you check this table, you will get it. So now if the overall depth of the slab is more than 300 mm, so you can imagine the slab thickness, if it is more than 300 mm, then the K value is 1. But if you reduce the slab depth, so the overall depth, now if the overall depth of the slab, if it is 275 mm, so in that case the K value is 1.05. So if you reduce the depth of slab, basically the K value is increasing. So in general, our slabs in a structure normally we provide 150 to 200 in this range. So now you can see K value is very high compared to more than 300, it is 1, whereas if you increase or if you decrease the depth of the slab, K value is increasing. So what does that mean? That means that tau c is the total strength of shear strength of a concrete. So it's multiplied by K. So K value is 1.3. So whatever shear stress is there, it will be increased 1.3. So that's why if you provide smaller diamond depth of slab, basically that type of concrete will take more shear strength. It has more shear strength. That's why stirrups may not be required. So from this table, basically we'll get it at different depth values. What is the shear stress applied, or what is the shear stress capacity of the slab? If the shear stress capacity is more than the shear stress applied on a slab, then we do not need to provide the stirrups on a slab. So in general, we always avoid to provide the stirrups on a slab. So now, before designing, we have to do the structural analysis, right? So what is structural analysis here? So structural analysis means like slab will be there, right? So now we understood what is now slab. So slab basically, in this lecture basically we will be discussing the one-way slab. So one-way slab means one dimension. For example, Lx is very high compared to very high compared to Ly, for example. In that case, it is a one-way slab. That means the designing will be very similar to the beam design. Okay, so in one-way slab, okay, I think this is almost two-way slab. Let me draw it one-way slab. So one-way slab means one dimension will be very high compared to other dimension. So let me draw it here. So this will be the one-way slab. So in this lecture, basically we'll be focusing on one-way slab more. In the next lecture, we'll be discussing about the two-way slab. So in the one-way slab, basically one dimension is very high compared to another dimension, right? That is one-way slab, and this shorter axis will always bend, right? In the one-way slab that we already seen. That means the design of this beam one-way slab is very similar to a beam design. So what we'll do in the slab design, basically we'll consider a beam, strip wise. Okay, so this is a beam, we can consider it while designing a slab, but the width of the beam is per meter, means 1 meter. And this is a one-way slab we'll be designing as a beam. Just only consideration we'll do it is the width of the beam will be considered as a 1 meter. Okay, so whatever reinforcements are required, that in this beam, in the strip of this beam, that will be find it out, and that is for the 1 meter width. Now, next meter, 1 meter width, same reinforcement will be provided. Whatever we get it here, same will be provided here, 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 like that. Entire slab will be providing. So that's why one-way slab is very similar to the beam design what we discussed earlier. The only difference here is that the width of the beam is 1 meter. So this is 1 meter beam we'll design, and then we'll just replicate or multiply the same design into other portions. So now before designing, we have to find it, we have to do the structural analysis. What is structural analysis? Basically, we have to find it out the shear force and bending moments in a structure or in a slab. How much shear force or bending moment generated on a beam, that we have to do it. So that you will get it in the IS 456 table number 12. If you open IS 456 table number 12, there the bending moment coefficients are actually given to us. Although in a rigorous structural analysis we can do it in this beam or in this slab, basically whatever loads are applied, that we can apply it and we can find out what is the bending moment distribution and the shear force distribution. That we have done it in the structural analysis course. But that is very much long process, means every time if the dimension or the load is increasing or decreasing, we have to do the same structural analysis every time you have to find out bending moment and shear force. But what our IS code says, IS code specifies few coefficients like bending moment if a UDL is acting on a slab, then these coefficients you can consider for designing. So what is this bending moment coefficient? You will get it in the clause number 22.5.1 IS 456. There, ready-made values are given for bending moment as well as shear force. So no need to do the structural analysis from the scratch. We can just use this table and you can find out what is the approximate bending moment and shear force applied on the structure. So what is this table? So type of the load, which type of load is acting, maybe dead load and imposed load. For that, span moment, so near middle of the end span, that much is the moment, 1 by 12 W L square. Whereas at middle span, at middle of interior span, this is 1 by 16. So as I mentioned in the earlier, in the first slide also, if you consider a beam or a plane of a building, so this may be a plane of a building. Okay, these are the columns. Multiple columns will be there, and multiple beams also will be there. And all the junctions you have one column. So here one column, here another column, here another column, like that multiple columns are there, right? So now you can see that how many slabs are there here. So here 1 2 3 4 5 6 7 8 9, total 9 slabs are there in this plan. This is a plan of a building. So here total 9 slabs are there, and each slab, if you see, if you consider this slab, so in this slab one side is continuous, this side also continuous, whereas these two sides are discontinuous, right? Similarly, if you consider the middle span, then this side is continuous. This all four sides are basically continuous for this middle, middle slab panel. Similarly, for here also, three sides are continuous, whereas one side of the slab panel is discontinuous. So, based on which location the slab panel is, that corresponding value we have to take it. For example, you want to design this, maybe this slab, corner slab. So in that case, you know, this one end is discontinuous, this end also, this two end is discontinuous. So at the span moments are given near to the middle of the end span. So this is the middle of the end span. So when you design there, how much is the value? 1 by 12 WL square. So that will be the maximum bending moment. Whereas at the middle of the interior span, so interior span means this is the interior span. So in that case, middle of the interior span, this span, the value is 1 by 16. Whereas this span, it is 1 by 12 because it is a end span. Whereas this is the intermediate, middle span. That means we can consider it 1 by 16 here. Okay, now at support next to the end span, so this is another value. So like that, from this table basically we have to take the appropriate values and we'll get the very simple, no need to do the structural complete rigorous structural analysis. From this table basically you can find it out what is the approximate bending moment and shear force in this slab. So these are the bending moment coefficients, and in table 13 you will get it the shear force coefficients. Okay, so from there we get it the structural analysis part. So now we'll see what are the design considerations we have to take care while designing our slab. So first is effective span. What is the effective span of a slab? So now we understand, right? So if this is a slab and the four sides are columns, four columns are there. So now what is the effective span? Effective span means L effective, this one. Either length is from corner to corner distance or from support to support distance. What is the L effective or effective length of the slab? It is a one-way slab, means only one shorter side we will be considering L effective. So how to compute that is, you will get it in the clause number 22.2 IS 456, that computation, how to find it out effective depth, that you will get it. So this table basically you will get it in this clause. So if you are designing a simply supported but not built integrally with the support, so in that condition the effective span is lesser of clear span plus effective depth of the slab or center to center distance of the support. So whichever is less, that will be the effective span. That is for first case. Now if it is a continuous slab, so in that case it is also same effective span. So like there in the different conditions, if it is a frame, then center to center distance will give you the effective span. So depending on the conditions, which panel you are designing, that's what I mentioned, right? In a slab, basically this slab may be a corner slab or maybe an intermediate slab or whatever with the boundary conditions. Depending on the support conditions, basically effective span also varies. So from this table and from this clause, basically you have to find it out what is the effective span. So first A was effective span. Now B is what? Effective span to effective depth ratio. So what is effective depth? Effective depth of a slab, right? So slab, as I mentioned, it is very one-way slab is, let me draw it. So this is a one-way slab, right? One dimension is very large. So LX and LY. So one dimension is very large compared to another dimension. So one-way slab means basically we design a beam, something like that beam, and the width of the beam is basically 1 meter. So that is the only difference, one meter or 1 unit, whatever it may be. And that beam basically we are designing. So if you see our beam design, how the beam design looks like. So this is simply supported beam. So L effective means this is L effective, right? That we discussed in the beam design also, center to center distance or whatever it may be. And then effective span to the effective depth ratio. So effective depth means whatever is a small d, right? Small d we call it effective depth in the beam, right? Same configuration, same name here also. Okay, so L effective by uh, effective depth ratio, you will get it in the clause number 23.2.1 A to E IS456, you will get it, because if you are designing a cantilever slab or a simply supported slab, so initial values you will get it in this clause. This is our starting point. Now number C is nominal cover. Nominal cover, as I mentioned, we have to keep some space at the bottom, that is we call it cover. That similar thing what we discussed in the beam also, that you will get it in this clause, what we should provide the minimum cover that is mentioned here. Now minimum reinforcement in a slab, so as I mentioned in the beam also, there are minimum reinforcement, maximum reinforcement. Here also in the slabs also we have the minimum and maximum reinforcements. So what is minimum reinforcement, how much is allowed to provide in the structure, in a slab, that is in this clause you will get it. So both in one ways and two ways slab, the amount of reinforcement, in either the direction shall not be less than 0.15 and 0.12% for the total cross sectional area of mild steel. If you are using a mild steel, then or Fe250 grade of steel, then minimum you have to provide is 0.15%. Whereas if you are using Fe415 grade or Fe550 grade of steel, then minimum you have to provide is 0.12% cross sectional area. That is as per our IS clause, you have to provide it anyway. Then number E is maximum diameter of the reinforcement bar, because we have to provide reinforcement also, right, in the bar. Reinforcement bar in the we have to provide in the slab. So that is how much we can allow maximum diameter of the reinforcement bar. That is the maximum diameter of the reinforcement bar is one or two A slab shall not be exceeding 1/8 of the total depth of the slab. Means total depth of the slab, how much we get it. Maybe if you get total D value is, for example, 120 by 8, which comes out to be 15. Yeah, so 15, so 15 mm, so maximum allowed is 15 mm bar. Okay, so in that case, if the D or the depth of the slab is 120 mm, then maximum allowed diameter of reinforcing bar in this slab you have to provide is 1/8, means 15 mm bar. We should not allow more than this. Now maximum distance between bars, because if you look how we provide the reinforced bars in a slab, so something like that we provide, right? This type of bars we provided on a slab. So what is this distance? So that distance also code is specified. It should not be, whichever is less, 3 times the effective depth or 300 mm. Whichever is less, that we have to provide it, is the maximum distance between the bars. That in this clause basically you will get it. So please open this clause and read it entire paragraph. What they mentioned it. So that is the basically the 6 design considerations we have to take care while designing the slab. Corresponding to the clause number also mentioned, please check the clause number and read the content and do the design. So now we'll see a design of one-way slabs. What are the different steps to design of one-way slabs? So from basic scratch we'll be starting. So now first step one is selection of preliminary depth of the slab. So what now we understood, one-way slab is nothing but a beam design, right? Because one-way slab means it is one dimension is very long compared to other two dimensions. That means basically we are designing a beam, and so beam only difference is it is 1 meter width beam designing. So whatever we get it here, how much reinforcement, same will be repeated again in this same reinforcement will be provided in each section, right? So that's how the one-way slab design happening. Basically we are designing a beam, and then beam we are replicating into the entire length. Okay, so our first beam design, if you remember, beam design was something like that. So this is a beam, and it is resting on two supports, and we have to find it out what is D, right? Depth of the beam. So here basically it is preliminary depth of the slab. We have to find it out. So preliminary depth of the slab, we have to select it. We have to, based on our past experience, or our code also said some starting point to guess, initial guess what could be the depth. So based on our past experience, we could choose the initial D, and then we check it in the other steps whether our D is sufficient to take care of the loads or not. So the selection of preliminary depth of the slab can be done based on our past experience, as well as our code also given, right? Some the effective span by effective depth ratio, some ratios are given in the code. So based on that ratio, we can initially we can assume some D value. Now step 2 is dead load, the design loads, bending moment, shear force from this IS4 that I mentioned last slide only. Table number 12 and 13, that coefficients are given, bending moment and shear force coefficients. So based on that we have to find it out, the design shear force, design bending moment, all these things. That is our step 2. So step 1 is basically we are finding out the D value. Step 2 is we are finding out the loads, bending moment, shear forces, everything. Now in the step 3 we have to check it whether whatever D we have assumed here, that is sufficient or not. In that step 3 basically we are checking the effective depth and total depth of the slab. So how we have to check it? So in the step 2 basically we know what is the bending moment, is not it? Maximum bending moment coming into the beam or coming into the slab. So mu limb we know, R limb, so same whatever we discussed, resisting moment, R limb we discussed in the beam design. So same R limb also we know, B is basically 1 meter width of the beam. So from this expression we know mu, we know R limb, we know B, we can find out what is D. So that D, if it is less than whatever we have assumed earlier, then our beam is safe. If this D is more than whatever we assumed at the step 1, then again we have to increase the depth of the slab. Okay, then again process will start from 1. So now if it is satisfied in the step 3, then we'll go to step 4, depth of slab for shear force. So then we have to check it, the shear force whatever is applied into the slab, that is sufficient, means whatever concrete slab we provided, that slab whether it is sufficient to take care about the shear forces or not. If it is not sufficient, then we have to increase the D again. That is step 4. And step 5, now determination of area of steel we have to compute, because we have to provide the reinforcement, right? Tension reinforcement at the bottom, compression reinforcement at the top, same thing what we did in the beam design. That we have to find out what is the area of steel. So using the same formula in the beam formula, what mu is equal to 0.87 FYAST into lever arm. So exactly the same formula, beam formula, we have used here also, and from this expression we find out what is the AST, area of steel required. That is step 5. And then in the step 6, last step, basically selection of diameter. Once you know AST value, means how much reinforcements you have to provide at the 1 meter width, that then you can find it out how much diameter of reinforcement we are providing and what is the spacing of reinforcement. That also you will get it in the clause, some specifications you have to maintain. So these are the total 6 steps to solve any one-way slab design. So this one you can see the detailing of reinforcements. So when we provide the reinforcement in a beam or a column, that actually we call it is a detailing of reinforcement. Okay, so in details we are giving everything, what is the distance between each bar and all. So basically in this slab design, one way slab design, basically these are the typical bars we provide. So here you can see that B1, B2, B3. So 3 is B means actually bottom bar. B means bottom we are providing the tension reinforcement at the bottom. So now you can see B1 is from here to here, entire full span from here to this support to another support. Whereas B2 is starting from certain distance. From here to it will continue up to the support. And B3 is basically this vertical line, y-axis line. Y-axis line is B3. These are the bottom reinforcement. At the bottom basically we are providing B1 plus B2, you can see both along the axis, whereas B3 is basically about y-axis. Okay, so this is one type of bar, bottom bars we are providing. Then we have to provide the top bar also. Top bar we call it T1, T2, T3, T4, like that. So T3 is actually top bar which is provided at the support. Now you may ask why this is only at the support. Now if you see the bending moment diagram of this beam, so let me draw it here quickly. So bending moment diagram for this beam will be something like that. So at near to the support you will have the negative uh, bending moment and something like that positive. Okay, let me erase this part. Yeah, so negative and then positive, then again negative, something like that. So bending moment diagram for this beam or for this slab will be something like that. So you will have negative bending moment and middle you have the positive bending moment, right? We discussed earlier also. So because of negative bending moment, basically the we have to provide the reinforcement at the top, as we discussed earlier also, because here near to the support the bending moment is negative, so we have to provide the reinforcement at the top. That's why only near to the support we are providing T3 top reinforcement, whereas at the center of the span the maximum bending moment is actually center of the span, negative bending moment, positive bending moment means tension reinforcement is we have to provide at the bottom. So that's why we provided B1, B2, both are as a tension reinforcement at the bottom. Okay. So again, the bottom here, if you see, the negative positive reinforcement is at the positive bending moment is actually middle of the span, whereas in this side it is negative bending moment. So whatever bar we provided at the center of the span, that bar is not required near to the support, because near to the support the bending moment is negative. That's why we provided T3. That's why B1 is continued towards the support, whereas B2 is curtailed up to this point, because B2 is what, bottom bar, right? Bottom bar. So bottom, after certain point there is only negative bending moment, right? That's why we provided T3. There is no positive bending moment, so that's why no need to provide B2 from left, from entire length. So that is B1, B2, and B3 is the vertical, I mean the about y-axis minimum we have to provide it anyway, that is B3. Similarly, here if you see near to this support, we have the negative reinforcement, negative bending moment. Because of that, the bending will be happening at the towards top fiber. That's why T1, T2, T4, all these things are provided near to the or at the support itself. Because here you will find the negative bending moment. That's why it is top reinforcement is provided here. Similarly, again in this span here, you will have the bottom reinforcement. That's why you have B4, B5, B6 bottom reinforcement. So near to the support or at the support always we provide top reinforcement, whereas at the center of the span we provide the bottom reinforcement. So these are the different types of reinforcements you will see in a slab. Okay, so B1, B2, B3, whatever I just explained, same thing are mentioned here also. So now let's solve a numerical problem, or we design a one-way slab quickly. So what is the question here? So question here is design the one-way continuous slab shown in the figure. So this is a figure subjected to uniformly distributed imposed load of 5 kN per meter square using the M20 and Fe415 grade of steel. The floor load of the floor finish is 1 kN per meter square. The span dimension is shown in the figure are effective spans. Whatever it is shown, 300, 3000, 3000, these are all are effective span. The width of the beam or width of the support, actually beam support, is given as 300 mm. So this entire slab is resting on a beam, right? All four sides we have the beams. So that beam is basically, so here what this is one span, this is another beam, another sorry, this is one slab, another slab, another slab. Here total three slabs are there. Okay, so and all the slabs are resting on a beam which is 300 mm width. So the load is given, how much load is coming in this slab. So which is uh, floor finish is 1 kilonewton per meter square, and the live load or the imposed load is 5 kilonewton per meter square. So we have to use M20 and Fe415 grade of steel to design the one-way slab. Why it is one-way slab? Because how to find it out? Although in the question it is given one-way slab, but if it is not given also, that also then also you can compute whether these slabs are one-way or two-way. Because our formula is what? Ly by Lx, you have to find it out. So here this is one slab panel, this is another slab panel, this is another slab panel. So there are three slab panels. So let's consider this first slab panel. So here Lx is how much? 3000, right? So Lx is 3000. What about Ly? So Ly is 6500. So it is 6500. So how much it is? So it is something like 2 point something 25, right? 2 point, maybe 2.2 or something. So it is more than 2, right? So it is more than 2, that's why it is a one-way slab. So one-way slab means if you compute Ly by Lx, if it is more than 2, then it is a one-way slab, right? That is our by definition. So slab 1, slab 2, slab 3, all are basically one-way slab. So we have to design this one-way slabs. That is our question. And load is given to us. 5 kilonewton is the imposed load, and 1 kilonewton is the floor finish. Floor finish means the tiles and all marble, stone and all we provided at the floor, right? So that is also 1 kilonewton per meter square floor finish is coming. Anyway, So our step, so we discussed in the last level, so there will be total 6 steps. So first step is selection of preliminary depth of the slab. So preliminary depth of the slab, how we can compute? So the IS 456, if you go to clause number 23.2.1456, there you will find the basic value for the span to the effective depth ratio is given to us. Span to the effective depth ratio for the slab having simply supported at end and the continuous at the other end will be this much. So we see just in the question how it is given. So the slab was basically one end is continuous, right? This is the slab question given to us. So this end is cantilever. So this end is cantilever, whereas this end we are designing this panel, right? One panel, two panel, three panel. So three slab panels are there. So all panels are actually same, right? The same loads are acting same dimension anyway. So if you consider this panel, panel number one first. So here, if you see this left hand side, you have the support, whereas right hand side is continuous, right? So left hand side is basically cantilever side, whereas this one is continuous side. So that's why if you go to IS clause number 23.2.1, in that case for the simply supported case it is 20, and for the cantilever, sorry, for the cantilever it is 20, and for the continuous it is 26. So this ratio is preliminary for computing preliminary depth of the slab. This ratio you will get it in this clause, IS clause 23.2. So this by 2 with 23. So for this slab, effective span by effective depth ratio, you can consider it as a 23. So again, in the next page of IS 456, if you go page number four, figure number 4, IS 456, some modification factor is also required. So whatever 23 you got it, that also we have to multiply it with modification factor as per our IS code. So how to find out modification factor? That modification factor basically from this figure number 4, basically you will find a graph. So from that graph, percentage of steel and Fs means what is the steel stress. So from that you will get it what is the modification factor. So in here we understood, right, minimum we have to provide is 0.12%, but normally we provide 0.5 0.6%. So let's assume we provide 0.5% steel in the slab. So based on 0.5% steel and Fs 240, we get it modification factor 1.18. So from this graph IS 456 figure number 4, please check it, you will get a graph. So from there 1.18 we got a modification factor. So therefore the minimum effective depth is 3000 is the effective span by this factor, right? Span by depth ratio is given to us. So by 23 into 1.18, 1.18 is the modification factor. From there we got it 110.54 millimeter is the depth of the slab. Okay, so this is preliminary depth based on some equations we got it, although it is not final, it is a preliminary. So let's take as effective depth D is equal to 115 mm with a cover of 25 mm. Clear cover you have to provide it, right? That is 25 mm. So total depth D is 140. So you can imagine 120 also, no problem. Or maybe someone can use 130, 140, whatever it may be. If it is a safe, the beam design, if the slab is safe, then whatever design you make, it is correct. Okay, so in this problem, basically, I have considered D value is 115. From where we got it 115? We got actually 110.54. We just make it round figure to next 5, multiplication of 5, 115 millimeter, and clear cover is 25 mm. We provided, so total depth of the slab is 140 mm. So this is step 1 is over. Now step 2 is design load calculation, load bending moment and shear force you have to compute. So now design dead load of the slab 1 millimeter width, because I mentioned, right, this is a beam, simply one way slab is nothing but a beam design. So the only difference here is you have to consider the dimension, the width of the beam, width of this one is as a 1 meter, right? So that's why 1 meter width we considered it. Dead load of slab we're considering 1 meter of width because the beam we are considering is 1 meter is 0.14, or 0.14 is what? Depth of the slab, right? Depth of the slab multiplied by 25. 25 is the what? The density of the concrete, 25 kilonewton per mm square, mm cube. So if you multiply it, you will get it 3.5 kilonewton per meter. So dead load from the floor finish is given to us 1 kilonewton per meter, and the total factored load total factored live load is how much? 3.5 plus 1, 4.5 multiplied by 1.5 is a factor of safety. So 6.75 is total dead load, factored dead load. And factored live load is given to us 5 kilonewton per meter multiplied by 1.5 is what? Partial safety factor. This is 7.5. So how much is the total factored load? This plus live load plus dead load 14.25 kilonewton per meter is the total factored load acting on this beam. So now for maximum moment and shear force, that coefficient as I mentioned, IS456, table number 12 and 13, you will get it, the maximum uh, coefficient value. So for the positive moment, maximum positive moment, it is WL square by 12, right? From this 1 by 12 we got it from this coefficient table. If you open table number 12 and positive bending moment in the mid span, it is 1 by 12 it is written. So 1 by 12 means WL square by 12. So that is the maximum positive bending moment. And in case of maximum negative bending moment, you will get it, the coefficient from this table 12 is 1 by 10. So 1 by 10 means WL square by 10. Okay, W is what? 14.25 into L square means 3 into 3 square by 10. So 10 we got it from this table number 12. And this is a maximum negative moment. And maximum shear force, we get it 0.4 is the factor or coefficient from the table number 13 from IS456. So WL into coefficient, you get it this one. So now in this slab, basically maximum positive bending moment is this much, maximum negative bending moment near to the support is this much, and the shear force is this much, maximum shear force. So whatever design we have to make, our slab should withstand that much bending moment and this much of shear force. Now in the step 3 is determination of effective and total depth slab. So whatever we have considered that 100, 115 is the D. Now we have to check it whether it is fine. How much D is required. So mu lim we know, just in the previous slide we know how much is the maximum bending moment applied. And R lim similarly, whatever same computation for M20 and F415, R lim we got it 2.76 Newton per mm square. Please check the beam design video where we discussed about R lim. So if you give you the D value, and if I give you the M20 and Fe415, you will get R lim value is 2.76. Okay, so from this mu also we know, from this expression mu is ours 12.825, right, into 10 to the power 6. By this value we will get what is the D value. So D value comes out to be 68.17. So minimum D or depth of the slab is required 68.17. How much we provided? We provided in the step 1 is 115, right? 115. So whatever we assume, so it is fine because D minimum required 68.17. We provided 115 mm in the step 1. So whatever we assumed at the step 1, this is fine up to this point. So this check is done. Step 3 is over. Now step 4, depth of the slab for shear force. Whether this 115 mm depth, whatever we provided, whether that depth is sufficient to take care about the shear force or not, that we are computing in the step 4. So again in the table 19, if you go, tau c value will be 0.28 Newton per mm square for the lowest percentage of steel in the slab. If you go to IS table 19 IS 456, there will be a table in that tau c lowest minimum shear stress value is actually 0.28. So whatever concrete and steel is there, if you take even the lowest percentage also, lowest percentage of steel, that grade of steel and concrete also will give you 0.28 Newton per mm square shear strength capacity. So, but here in this problem, let's compute how much shear stress is applied here. So further the depth, our depth is 140 mm, right? Depth of the slab. Let us use coefficient K value. So as I mentioned earlier also, K value from this clause number, it is 1.3, it comes out. So tau c value, whatever we got it 0.28 multiplied by 1.3 K value, we will get it 0.364. So our slab can take that much shear stress. Now we have to find it out how much shear stress is applied on the stress. If applied shear stress is more than this, then we have to provide the stirrups. Again, stirrups is not allowed, so we have to increase the depth. If the applied shear stress is less than this value, then everything is fine. No need to do anything. So now from the table 20, IS456, tau c max will give you 2.8. So from our problem, How much is the applied shear stress? It is maximum shear force by B into D, right? Maximum shear force BU, in the last slide we computed 17.1 divided by B into D. B is what? B is 1 and D is 115, right? D is 115. So which is comes out to be 0.14 Newton per mm square. So applied shear stress is 0.148 Newton per mm square. Whereas our slab can take up to that much shear stress, 0.36. So whatever our slab can take, it is very high compared to applied shear stress. Okay. So depth of 115 millimeter is acceptable. So there is no problem. So step 4 also over. So now step 5 is determination of areas of steel, AST. Now we have to find it out. So now for the maximum negative bending moment, which is happening at the center of the span, which is based on this formula, right? We already used the same formula for the beam design also. Okay, mu equal to 0.87 F, FYAST and then the lever arm. So from there you compute what is the AST value. So from there, if you compute, we'll get AST value is that much for the maximum negative bending moment. Now for the maximum positive bending moment, this value we got it right in the step 2. Same value. For that we need AST value is 270.61 mm square. So for the positive bending moment we need this much AST and negative bending moment we need this much AST. So step 5 is also over. So now in the step 6, distribution of steel bars along the span LY. So distribution of steel band. So minimum we have to provide it at the along the Y. So whatever we discussed, we computed AST in the last slide. That is for the x-axis, towards x-axis. But towards y-axis also we have to provide the minimum reinforcement. That is 0.12%. That also we have seen in the first few lectures, first few slides in this lecture. 0.12% minimum we have to provide it. So 168 mm we have to provide it for both positive and so for negative steel, basically 10 mm diameter and 230 mm center to center distance, AST is 341. Okay, so which gives PS, the percentage of steel value is 0.29%. So for positive reinforcement we are providing 8 mm bar at the rate 180. So you can use 12 mm diameter bar also at the rate this also will be changing, right? So you can use 230, 250, whatever based on your calculation, whatever distance it comes. So in the last slide, basically what we computed AST value, right? So we computed AST value. So this AST value is for per 1 meter width of the beam. So this AST value, from that we compute 10 mm bar is required, right? So 10 mm bar if you provide, then what could be the spacings? So the total thickness is 1 meter. From that, so how many bars we need to provide for the 10 mm bar? So 10 mm bar it comes out to be 4 number of 10 mm bar we have to provide it, and total width available is 1000 mm. So maybe you have to provide maybe 200 spacing in between each bars. For example, but for here it comes out to be 230 mm center to center spacing. So which negative steel we have to provide it that much, positive steel 8 mm bar 180 center to center spacing, that will be comes out to be like that. And for distribution means about the y-axis. So reinforcements are provided along the x-axis as well as along the y-axis also. So y-axis means we call it distribution steel, that also 8 mm bar at the 250 center to center we have to provide it out. So that is the distribution. Now selection and diameter and the spacing of reinforcing bar, that is also the maximum diameter, how much you have to provide it. So as per our IS code, it should be 1/8 times, right? 1/8 times of D. So D is how much? D is 140, right? 140 total depth of the beam, depth of the slab. So 1/8 means 17 mm. So maximum we can provide is 17 mm bar for that, for the design of this slab. Okay, so whatever we have provided, that is fine. We have provided less than 70 mm. And the spacing also, spacing of bars means we have to provide longitudinal bars as well as transverse bars, right? So this is, we call it spacing, whatever is the spacing. So this spacing has two criteria. It should not be more than 300 mm or 3D. Which one is less, that you have to compute. So 3D means how much? 3 into 140. 3 into 140 means 420 or 300, whichever one is less. So 300 is less, so whatever we provided center to center distance, all are less than 300, so that is also fine. So step 6 also fine. Now in the last step, basically you have to draw whatever we got it till now, all the parts we have to show it in a diagrammatic manner, so that the site engineer can build the slab in a site. So all the bars, whatever we got it, T1, T2, T3, tension reinforcement at the bottom, compression negative reinforcement at the top. Same thing, whatever we got it, just 10 Tor bar, there 230 center to center, 8 Tor bar, just now we completed these values. So that we have to draw it in this diagram, and ultimately this diagram will be given to the site engineer. So this completes basically one-way slab design. So in the next class, we'll be discussing about the two-way slab design. Thank you.